In the previous video, we learned e-commerce simulation and we get into oversold problem. It is a very famous transaction problem. So every distributed system learning or every parallel processing learning starts from the transaction problem. So we have seen the problem. Hope you understood the problem very well. And this is the extract from that actually. So what actually happens? There are multiple threads executing this process user activity function. And in two threads, if user is actually entering into a buy state, for example, Alice wants to buy iPhone. Parallelly, Bob also wants to buy iPhone. And Alice reads the inventory stock, inventory value, and Bob also reads inventory value. And both are saying only two. And Alice transaction complete. And parallelly, Bob's transaction completes. And Alice updates the inventory from the locally available stock value. And Bob also does the same mistake. Even though two different threads reducing value 1 and 1 here, the final value should be 2 reduced in the inventory. It is not happening here. So what are we going to do here is, we are going to allow parallelism in these two operations. When user is reading a spec of a phone, we will let other user read a spec of a phone. 10 users can read spec of a phone in parallel, no problem. When user is comparing two phones, okay, other user compare two phones, because they are not going to update the inventory. These are all stateless operations. They are only reading passive data. They are not modifying any inventory data. So in the process user activity, we are going to allow these two actions, read spec and compare, to be in parallel, but we are going to make the buy operation sequential. So what do I mean by this? When somebody is buying one phone, if Alice is buying a phone, it means Alice transaction is in process. So Alice has entering credit card details, she's waiting for OTP and everything. When that process is happening, I don't want anybody else to buy that product. So if Alice is buying a product and Bob wants to buy a product, Bob will be waiting in a queue. So multiple threads are going to be running in multiple different hardware. But when they come into this code path will run at most at only one thread at any point of time. Even though there are 10 threads, not any two threads can execute this part of the code in parallel. How are you going to achieve that? So if you do that, it is going to solve the problem, right? Because this is going to be executed with only one thread, this entire section. So when I read the inventory, the value is the current inventory. And when I update the inventory, in between nobody else read the inventory. Because when Alice thread read the inventory and Alice is processing the transaction, until Alice completes the transaction and update the inventory, until this point, nobody else is going to enter into this code. It means nobody else is going to read the inventory. That's how I'm going to maintain the sanity of the program. So how am I going to achieve this? For that, I'm going to use lock. So I have created the program here. It is a copy of the same code, additionally some locks. So for locking available in the thread library itself. Everything else is same. I'm creating a new lock called inventory, like it is a global variable. So lock is created using threading.lock. So lock name is inventory lock. So note everything else is same. The timestamp with the code is almost same. Only thing is you add a new line, inventory lock equal to threading.lock. And in the process user activity, read spec is same, compare is same. In the buy action, we are actually taking the lock before reading the inventory. So this is the place we take the lock. Let me put a gap here, and so it will be like I'm taking a lock here, and after taking a lock, I'm reading the inventory here. Then I'm printing user wants to buy, then checking the stock availability, then actually waiting for the transaction to complete, the money to credit to my account, then updating the inventory. After doing all that thing only, I am releasing the lock. So here, don't worry about the wait function. I will come to this in a moment. So this, don't need to worry about it for now. So you can see this is a lock acquisition. I'm taking the lock at this line, and after taking a lock, here reading the inventory, then doing the transaction, here writing back the updated stock value into inventory, then only release the lock. Okay, and this lock, inventory lock, is a global data. So I created it here at the global state. So this data value is actually shared across all the threads. We have 10 users, so there are 10 threads, and every thread, when they are coming into the buy section, they have to first take the lock. And the lock is a special property. If somebody has taken a lock, the other thread cannot take the lock. So this actually creates a sequential here. So everything can be executing in parallel, but when they enter into the buy section, that thread has to take the lock. If Ali's thread already taken the lock, Bob thread has to wait for the lock to be available. So when the lock will be available? When Alice thread actually releases the lock. So when Alice thread is actually processing the transaction, Bob thread is actually waiting for the lock because Bob thread is trying to acquire the lock. And when Alice thread completes the transaction and releases the lock, by the time the inventory value is already updated. So now if Bob thread acquires the lock and reads the inventory, the value is correct. It is not 2 anymore, it is just going to be 1. So like this, by introducing a lock, we are creating a sequential. So every data, every instruction between this lock acquire and lock release cannot be running in parallel. So we created parallel processing, we created multi-threading to run the process user activity in parallel. But now we are making the function sequential again. But we are not making the full function sequential. So we have 3 use cases: read, spec and compare. We are letting these 2 operations to be in parallel. We are not affecting them. And this portion, only the buy portion, we are putting inside the lock. So the section between the lock acquire and lock release is called critical section. We will learn about critical section in a moment, but before that, let's actually execute the code and see whether it solves the problem. Okay, I have cleared it already. Let me run the code. Python e-commerce simulation with course log. Again, same problem. Let me copy it from here. Where is the JSON file? Yeah, here is this line. I will copy from here and put it there. Copy here. Okay, this is the line. I'm going to paste it. Directly paste on top. Worked. Nice. I have to import the path lib. Okay, import. Let me execute the code now. And still no. Why? Okay, I didn't save the code. Sorry. Run it again. Yes. Transaction started happening. It's going on. Alice wants to buy. Alice is still buying. The transaction is happening. Yes, Alice purchased iPhone 17 Pro. You can see clearly in between Alice wants to buy and Alice purchased iPhone 17. So it has taken 10 seconds. It is 388. It started. It completed 1389. In between, there are no other wants to buy transaction. Using the lock, we made sure no 2 threads get into the critical section, get into the buy operation in parallel. So when Alice wants to buy, we wait for Alice transaction to complete before letting Bob thread enter into the buy. So when Alice completed the purchase, then Bob wants to buy, then Bob purchase, then Frank wants to buy, Frank purchased, and Charlie wants to buy, Charlie purchased, Eve wants to buy, Eve purchased. So whoever wants to buy, the next message from the buy operation is purchased information from that particular user. So we don't see any interleaving thread messages here, right? So now if you see, we got, okay, our inventory, final inventory, we sold out Pixel 10 Pro, iPhone 17 Pro, we sold out everything. Nice. And we sold 2 Pixel 10 Pro. The inventory says like, yeah, from inventory, it got reduced to 2. Okay, sold 2. Yes, and we had 2 available, sold available 2, we had 3, sold 3. So we didn't oversell any product here. So this is what we wanted to do, right? We still achieved parallelism. If we have done that in sequential, maybe I need to write a sequence program to see how long it is taken. But because I writing it in parallel, the code actually executed faster. When a user wants to browse about the mobile, they want to read the spec. Usually people spend more time on reading the spec and comparing phones, right, than buying, because they are not going to buy multiple phones day in day out, but they are going to read about phones day in day out. So when they are going to read about the phone, compare the phones, it is going to be parallel, it is going to be blazing fast because it is going to run parallelly for users. But when they enter into the buy operation, suddenly it becomes sequential. So when a user wants to buy a phone, the system checks if anyone else is buying. If someone else is buying, making the new user be on the queue. When the first user completes the transaction, then only allow the second user go into and buy the product. We achieved it only by 3 lines of code. Introduce inventory like a global variable, and just above the critical section, acquire the lock, below the critical section, release the lock. Sorted. It's very simple. So if you understood the concept, you may have learnt about locks previously, but at this point, you saw the problem and you saw how the lock actually solved the problem, right? In the next video, we are going to see a disadvantage of this particular method, and we are going to find one optimized way to improve the problem little bit better. Hope you like the video. Please don't forget to give a thumbs up and share the video with your friends, and please subscribe to the channel for getting to know more detailed concepts like this. Thank you for watching.